The second talk of this session is going to be given by Naïm, Moussaoui, Remil from Inria. And Naïm is going to talk about termination resilience static analysis.
Thank you. So, hi everyone, thank you to be there for my presentation. Today I will present the work I did under the supervision of my PhD advisor Caterina Urban, and which is a static analysis for a new property called termination resilience. So let's introduce this static analysis through an example. We'll use through this talk an example, which is a function foo taking in input a variable x. Then it's assigning to z the value 10. And then we encounter a if-else block. Inside the if block, we have a while loop. While z is positive, it decreases the value of z by the value of x. And in the else block, while z is greater or equal than x, it first assigns to c a random integer from -2 to 1, and it increases the value of z by the value that has been generated. The if condition is now some dots. Let's consider it as non-determinism choice. Both blocks are possible. And in the context of termination verification or non-termination bug finding, we have a problem here because the both of the loop may diverge. The first one may diverge if the input value x is negative, less or equal than 0. And the second one also, if, for instance, all the random integer that has been generated are greater or equal than 0, because for the first case, the value of z will always increase, so it will always, the condition will always hold, and for the second loop, it's the same. So the question that we want to ask here in our work is which non-termination alarm is more critical? And to distinguish between them, we'll say that we want to be more cautious about the input value. We'll take somehow an adversarial setting and say that this one should not be trusted. And we can see that the first loop, the condition to diverge only depend on x, and just the input of this function can enforce a non-termination of the program. In our work, we formalized it as a property that we call robust non-termination, attesting that a non-termination bug is robust and then more critical. More or less formally, it is defined as the fact that there exist some inputs such that for all internal choices of the program diverge. Here, the internal choices correspond either to a deterministic statement such that the assignment to z, or the random integer assignment here. Our goal is to get rid of these critical bugs and to define and to do a verification of program attesting that there are not such critical bugs only depending on the input. And so the definition of the property that we want to verify is simply the negation of the robust non-termination, which we call termination resilience, and is again more or less formally defined as the fact that for all input there exists an internal choice of the program. There exists potentially multiple internal choices leading to the termination of the program. And this is the case for the second loop that we have seen. If, for example, the sequence of random integers that are generated are strictly negative, for a long enough sequence of iteration, at some point we'll exit the loop and terminate. And in our context, we'll say that this loop is safe because our property holds. You can think about this property as a termination property, but where we refine the notion of non-determinism inside our program. The non-determinism that is induced by the input value, we want to treat it as a mnemonic non-determinism. And for all other non-determinism induced by the statement of the program, we want to treat it angelically. And my contribution here, with this property defined, is a static analysis for this property. So as usual, in an abstract interpretation-based static analysis, and in static analysis, we want to define the semantic of the property to verify in a concrete point of view. And just here, I give you a global view on what we want to do. We want to start from the end of the program here with some final state that are depicted in purple. From there, we're sure that the program terminates and hence the termination resilience property hold. And we want to compute backwards through the execution steps how many execution steps are needed to terminate. The semantic, more precisely, is defined through a fixed point and defined a ranking function from program states to a world order set. Here we only use natural numbers. And as I said, we start from the final state with the value 0. For all other states now, they are undefined, they are not inside the domain of definition of our function. And then we try to go backwards through the predecessors of the defined states to find how to count how many number of steps are needed. So in the first step here, the possible predecessor are this state and this state. For the top one, 2 branches are possible through blue transition. Here, the blue transition represents the internal choices that in the formalism I call regular transition. And as I said, and as we saw in the property, we want to treat it angelically, and so only one branches is needed, but here, in any case, both lead to a final state, so we add it in the domain of definition. Here, we needed 0 step to terminate, so trivially, logically, we need 1 here. But for the branches at the bottom, 1 leads to an infinite execution. But as it's a regular transition, one where we can allow at least 1 transition toward the terminating state, we can add this state in the domain of definition. So you can see the link between the exist in the definition and the fact that here you take the infimum and you use the predicate transformer of the pre. Just to show you that we also consider just deterministic transition as regular, we can do 1 more step and add this program state in the definition with the value 2. We could not add the first state here because the branches were from where the transition to go toward a defined state are only input transition that I depicted in red, and they go to this defined state, but not to this one. So there is a possibility to diverge here. But if I continue, at some point, all the possible transition with the input transition leads to a defined state, meaning that all the choices through input transition are safe because we always terminate. And it's formalized through the fact that here we use the predicate transformer of the pre-tilde defined through a for all, and there was the exist here. And we use the supremum with the same idea of taking the link between a for all and a supremum as it's used usually in mathematics. So this semantics is sounding complete for the verification of our property, termination resilience, but as usual, it's not computable if you in the general setting, and we want to define an abstract semantic for that. This abstract semantic relies on an abstract domain that compute piecewise defined ranking function. And the soundness criterion here is interesting. We want to under-approximate the domain of definition of the concrete ranking function on the left and over-approximate its value, meaning that we infer sufficient condition for termination resilience, plus we over-approximate the number of steps before termination resilience. Internally, it's represented as a decision tree. The plot on the right represents a function defined when the value of x is negative and with the value 2. It's exactly how it's represented for the decision tree. Here, what we have, if the condition hold, we look at the leaf on the left, and we have a bottom. The bottom represents the approximation. So it may mean that in the concrete, it may mean that in the concrete we have robust non-termination, but we don't know, so we'll keep it undefined. And on the left, we have a value 2, meaning that in at most 2 steps, the termination of program happen. With this abstract domain, we do a static analysis. And as for the concrete, we start from the end of the program, and we go backward with a value 0. We have transfer function to handle if condition, where here, for example, it filters the domain of the program and reduce it, and increase at each step the value of the function. We have an assignment transfer function that can, for example, here extend the domain. And for the while loop, we do some iteration, and we have a widening operator that do some extrapolation and try to predict the global value of the ranking function. So my goal here is to give you some key idea on how we do the static analysis. And I will directly jump inside some iteration of the analysis where at some point here at the control point 9, after the evaluation of the transfer function for this assignment, we obtain a decision tree telling you that if z plus c minus x is positive, you don't say anything, you have a bottom. Otherwise, if the negation of the property holds, you terminate it at most 2 steps. Then, to do the analysis, we go backward, we apply a backward assignment on the tree, and this is where we need to handle some problems. So, to do the backward assignment, we will treat the partition represented by the decision tree independently. So we want to treat both paths where z plus c minus x is positive and when it's not. So we separate it in 2 trees. One telling you that here we have a bottom, and the nil telling you that here this part of the program state are not considered. Same on the right. The assignment, we apply it on the condition that resolve the inequality that we have on the top, and we obtain the new condition z minus x plus 1 is positive. We do it on the decision tree on the right. We obtain z minus x minus 2 positive, and we increase the value from 2 to 3. From there, we have applied the effect of a random integer assignment on both partitions of the program state. And what we want to do is to join the 2 new results. Before joining them, we need to unify them. It will be simpler. So we unify both trees with to have the same structure and the same path to talk about the same program state directly. And we obtain for the tree on the left this one on top left, and on the right this one on top right. And it's exactly the same trees. It represents exactly the same information if you take a look, because this condition on the left is still implied by this condition here. From there, it's really easy to join. We just have to do an induction on both trees, explore all the passes that are the same, and join the leaves. Let's see how we can do it. So the first 2 leaves that we want to join by the exploration is the bottom and the nil here. As I said, the nil represents the fact that here we do not consider these parts, and it's like when you analyze, for example, it's like having it's like analyzing an if-else block where you can keep the information that you obtain on the other branch if you are sure that the other branch is not reachable. So we keep the bottom, meaning that maybe the property hold, maybe it does not, and everything is the thing that is important is when you join a non-defined leaf and an undefined leaf. Here we have a bottom and a leaf tree that we want to join, meaning that on some precondition you may diverge, but for the other you're sure that you terminate. And as what you want to apply is a transfer function for a random integer, which is an internal choice that you want to trust, you will keep at the end the defined leaves. Whereas when you want to analyze, for example, just a classical termination property, you will have keep the undefined part. And it really shows that the important thing here is that we can use the partition induced by the decision tree and apply smartly some join to keep the information through the static analysis. For the last join, we also keep, as for the first one, the defined value 3. Then to finish the analysis, we obtain this resume 3, meaning that if the condition does not hold, termination resilience happen in 3 steps at most. When we go back towards the condition of the loop, we add it in the tree. Here you have the fact that if the condition of the loop does not hold trivial, you will in 1 step exit the loop. And after some iteration, you obtain a 2 tree that you want to widen. And here it's important that you see that here it's defined. It will not have been defined if we have used another join as the resilience join I defined. The widening, I will not explain it in detail. You just reuse a previous one for termination and do a linear extrapolation, which give you, at the end of the analysis of this loop, a fully defined tree, meaning that whatever whatever are the states before the program, before this loop, we are sure that termination resilience holds. So here, what I have shown is the analysis using the random integer, where we are sure that no, let me rephrase. So here I've shown how to use the resilience join to join partition from where we are sure that termination resilience holds and where it does not. And basically, we want to favor the one where it holds because we are sure that it's an internal choices. What we would like to do is to generalize it and apply it everywhere, some sense. The idea is to having a taint analysis telling you that does this statement depend on an input or not, and then internally you want to apply different join depending on that. The problem that we have here and why we cannot do it, so just maybe let's see the fact that here what we want to do, if the condition is on a random integer, we would like to join the fact that we have an alarm and a safe alarm and a bad alarm with a safe alarm at the beginning of the if block. But the problem is when, for example, you will have the fact that you change the condition with a square positive. Because it's not sound anymore, and because in the concrete execution, the second loop is not reachable anymore. And what we lack to generalize this resilient join here is a feasibility analysis. We want to be sure that it's feasible to reach the second loop such that you can join. Our static analysis has been applied in a prototype analyzer called raw function that is a fork of a previous one function. At some point it will be merged, I hope. The prototype is coded in HTML, not in HTML as depicted in the screen. We only analyze numerical program with signed integer with the assumption that we do not have any overflow. That's the only assumption that we have on the integer. And we have no assumption on the knowledge of the inputs with regard to the internal choices, in the sense that if you want to modelize the fact that an input has the knowledge of the previous internal choices, you just have to rewrite the program in another order, where the input appears in another orders. To evaluate our approach, we decided to see how we can reduce the number of alarms and attest how many alarms are less critical. So we took many non-terminating benchmarks. We are sure that non-termination happened, and from SVComp, from benchmark of Pulse, and from benchmark of survey by Shi and Hall at FSE on non-termination bug. And all of them, for all of them, we'll run our termination analysis and our termination resilience analysis. Of course, the termination analysis will always raise an alarm, and we have shown that for more than 65% of the termination alarm, we attest them as less critical because termination resilience holds. Just some word about some related works. So our idea came from some work on some safety properties and some runtime error bugs. The first one that we have seen is robust reachability by Giraud et al. The idea is exactly the same as robust non-termination, where they want to check that there exists some value for the inputs, such that for all internal choices, a buggy location is reachable. The other work is about runtime error, and they take the same approach, but they want to prove that the input cannot either silence or trigger a runtime error. So it's more refined. And here they use the idea of the taint analysis to do that, and we tried to apply it to a liveness property, and we decided to refine it with termination that led to termination resilience. An interesting word that I want to talk about just here is there exists some logic to express such properties, such mechanism. They call it analysis of open programs, where we do not put any distinction between the input are called closed program. And inside this property called alternating time-temporal logic, we can express robust non-termination, termination resilience, and also robust reachability. Just the idea behind it is a CTL property lived with this new notion of distinction between a set of players, in fact, and a set of other players. So some conclusion and future work. Oh, there is a bug here, I don't know why. So we have seen a way to refine the notion of termination in a new context, where you put some distinction between the input and the internal choices that leads to the property of termination resilience. We define a concrete semantic for that and an abstract semantic with a static analysis. And for future work, what I would like to do is to first work on the analysis of heap manipulating program. As we have seen, we do not have yet a way to analyze heap manipulating program. It's ongoing, and I hope it will be done soon. We have some preliminary on robust non-termination bug finding. In the implementation, it's done in some sense. It has to be formalized. So we have way to infer a robust non-termination bug. And as I mentioned, there are logics that interest me, and I would like to go toward the analysis of the alternating time-temporal logic. That should be okay to do because we can lift the previous CTL analysis to do that. And that's it for me. Thank you.
Thank you. We have plenty of time for questions. Do we have any questions in the audience?
Hey, thanks for the great talk. I was wondering about what's the motivation for termination resilience in the first place? So this differentiation between like angelically handling the random, for example, and yeah, you get the point. Why do we do this differentiation?
Why is the motivation behind the property itself, or why do you want to?
Like, what is this? What real world problem is this expressing? Kind of?
So as I said, it's what it proves. It proves the absence of its negation. That was the goal. We say that we should differentiate between some bugs that are more robust, more critical, that we want to attest, and we take the approach to verify its absence and not finding the fact that there are robust bugs. And the motivation is that you verify its absence. Then, when you want to apply it more concretely, you have to define. You can define in different way what are the untrusted input that you want to check. So it can, for instance, be for third-party library that you do not trust, some inputs. And also there is a rooted reason behind that on the static analysis. Because sometimes the transfer function, you don't have a precise way to abstract them. And so you abstract them to top, which in a numerical point of view. So a non-deterministic choice between -infinity plus infinity, if you want. And so that is analyzed as an internal choices, and it can raise some alarm, and you can, for example, discard them because it's only because of the static analysis itself and not the problem. So there are many reasons you have to, many motivations you can apply them in different way, but you discard some robust bug, you're sure that they do not happen, and you can, as we did, filter them.
Okay, thanks.
Other questions?
So can you say a bit more about the relation to CTL, and could you have taken their algorithm and done what you did, or maybe not?
So what I did not say is that as a CTL analysis I mentioned, use a decision tree analysis. So it's a previous one did by Caterina. And so what we could do is rely on the same idea that the decision tree gives you a partition of the states where the CTL property holds. And then you want to reuse the same idea of joining them, depending on what kind of statement you analyze. And so it will, there is, I think, a semantic work to formalize it, to be sure that it works, but it should be okay to lift our idea from termination to the CTL analysis to obtain the alternating time temporal logic analysis. Is it?
Yeah.
To answer your question. But there is needed to work. It's not straightforward. But that's my intuition.
So thank you for the nice talk. At some point you introduced this nil thing. And I was wondering about if you think of your abstract domain as a lattice, is this a bottom, this nil, or is it not quite a bottom? And what would be the concretization of this nil?
So that's a good question. So it disappear after each algorithm, each transfer. When we apply the abstraction of each transfer function, it can happen during the algorithm, the computation, but then it disappears at the end. So, and that's why it's not part of the lattice or the computation or anything. Yeah, that's it. It's just part of it. It's just that we have a decision tree that represents partition. We split it. We put a nil to say, oh, here it's not represent. You don't have to consider it. You don't have to consider it. And when we join at the end, it disappears because as you have seen, it always the other leaves always win over the nil, and so that's why it's.
Okay, thank you.
Yeah, good question. Thank you.
One more question.
So you mentioned as the future work analysis of heap manipulating programs. So could you be somehow more specific? Because that's in general a very big area with like many different approaches. And what do you actually consider like heap manipulating programs, like dynamic data structures or just like some pointer manipulation?
So what we want to do is go step by step. And like right now, what I'm considering is just sequential program where you have pointers. And I want to do a kind of points to analysis lifted with our domain. And that's what I have in mind. And for data structures, maybe we could like rely on like flat data structure directly, but the one that are inductive, no, it's not currently in the project.
And maybe one more question. So do you have some interesting examples for this, for the combination with the analysis of heap manipulating programs? Some nice programs that the properties that. So
I've sorry. Just with one step, with the step that I have in mind, I would not be able to analyze them. But when I've searched on the CV benchmarks, I have found some where robust non-termination holds. And they are usually drivers programs. And currently, I could not, even with the step that I have in mind, analyze them. But eventually, at some point, we'll have all the necessary work to analyze them. But it's need a lot of work to scale to have a bigger code-based analysis. But there are some on CVE that we can attest that robust non-termination hold, and we want to distinguish between them and the others.
And do you also consider like going for concurrent programs? Because there are some very interesting like concurrent data structures like skip lists, for example, when you would like to maybe check whether there are some, you want to have some termination guarantee there, right?
So the question is, I would like to, but I think it will not be for a short future.
Let's thank again Naïm.
Thank you.